and its time is 2030. Okay.
Mhm.
Now, this is the first page, and the page tells that let's talk about the sun. And we are very much inspired by the IUCAA refreshers course, and with that inspiration, we have developed a short video talk on sun. And this talk is mainly based on the talk delivered by Professor Tifarti on that sun. Now let's start about the talk. Now this is the lecture layout. The main points are why study of sun is important to us, uh, as we believe that it should be clear that why the study of sun is important to us, how long we studied the sun, what we know about the sun, and what we don't know till now. These are the basic points we think we should have to discuss. Now next, why the study of sun is important to us. Now this is important to us because to be aware of the influence of the nearest star, because sun is the nearest star and we don't know our origin till today. Our origin, what is the origin of our existence? How actual evaluation takes place and how we developed the human Homo sapiens. Where from we come? Are we developed on the Earth surface or come from some interstellar space? What is the origin of Earth? Now we know that the nearest, from the very uh, beginning of the civilization, every man and woman have witnessed that the bright sun at the morning, and nobody can ignore its presence because it is so bright, nobody can ignore its presence. That is, it ultimately draws its attention. And there is no way to escape from that because we are confined in the solar system and sun is our the nearest star and the only star around which we are revolving. Hence, our origin may be entangled with the sun and how it is to be disclosed and it is to be unearthed. And our present existence is very much entangled with the activities of sun and the presence of sun. Because we know without sun we cannot see, everything is dark, full of dark. We need artificial light, and to with generate we have to generate electricity or artificial light for luminance to see. We cannot see anything because hence the present existence to act for every activity is entangled with energy. Even our movement, everything is entangled with energy, and energy source, if we see the energy source and we ultimately reach to this nearest star, the sun, and we observe that our present existence is very much entangled with the sun. And not only it helps us, but it also has some threat on us. Hence, to know the existence of our future, for future existence, we have to know the threats also. Not only the how it helps us to exist, but also how what are the threats that will be fatal for us. For all these, we need to how every aspect of sun better, every aspect of sun better with reference to our context, and also need to have a better understanding about the evaluation of other stars in the universe as practical. Now, the effect of solar wind, we know that the solar wind is a charged particle, high energetic charged particle, they thrown out of the sun and outer surface of the sun, and they passed through the solar system, and they also pass uh, about our Earth, and the Earth is shielded by its magnetic field. And here is the influence of sun, the effect of solar wind, how it affects. It affects the all charged particles are flowing past the about the Earth, and Earth's solar magnetic structure acts as a shield, and the charged particle passes outside the outside this shield, and some of the charged particles. Okay, let me. And some of the charged particles are drained in the through at the boundary at the peripheral region of the magnetic field. That is, and they produce aurora at the polar region of the Earth. And these are the effect of charged particles. That is the solar wind on sun, and this is a this is a compromise. This is a competitive case because this is not a specific charge depend upon the solar wind. Solar wind, that is the magnetic structure of sun, and uh, the magnetic structure of the earth. It is a relative dynamics on which the exact amount of flux depends. Now, how long we studied the sun? And there is a debatable fact that how long we studied the sun. But if we put our logic, there is some evidence that the study of sun started from the very beginning of the before 800 BC. That is more than 2,500, more than about 2,800, 900 years before that. Some observation on Sunspot was there. But we know that there is no telescope was there at that time, and though recording may be there, but there is no some systematic observation, maybe, because it's still a debatable case, may be there for the observation, and the recorded systematic observation started only after about 400 years ago by the Galileo, and for the development of telescope, and he observed the sunspots and its motion, and very systematically at regular interval on daily basis, and he also noted down all the sunspots and its development, temporal development. Now, from that Galileo, and if we see the recent observations, we see that from the first century to the present, that is 1900 something, 1975, 65, or 60s to the present, we have NASA have several observations. NASA by satellite launching satellites, and some of them are Solar Orbiter, Parker Solar Probe, Solar Dynamics, Stereo, SOHO, IRIS, Van Allen probes, Magnetic Multiscale Observer, GOES series. There is a series of satellites from 1 to 2 from 1975 to 2001. Then RECI, and then Hinode. That is it's a joint operation by Japan, US, and UK mission. And all these are engaged to probe sun, to know the unknown, to unearth the unknown. They try to find out someone is devoted to the coronal region, someone devoted to the X-ray emission into the part, different spectrum region are focused to different spectrum region. But the recents are the Solar Orbiter. Solar Orbiter, they are very they are 8.5 solar radius. They are close to 8.5 solar radius. This is the distance ever reached by any satellite to probe sun, and we hope that much of the information will be available by these two, Parker Solar Probe and Solar Orbiter, especially. Also, SOHO is there. Now, we know that sun. What we know about sun? We know different types of things we have concluded different types of things from different measurmental and theoretical aspects. such as there is a collage that how sun is a star and how star evolves. There is a collage, and this collage is developed by Purvi, and he shared and he requested me that if you willing, you can share it in the lecture, and I gladly accepted it. There is a fine collage that we say that it's because nobody can observe this type of evaluation in its lifetime or a generations for few generations, but these are the diagram done out of different type of multi-spectrum observation and theoretical prediction and their verification. From that, we know that the gas cloud, there are the two paths. One is from main sequence, and it passes through red giant, planetary nebula, and white dwarf, and another thing, high mass solar system, it passes through supergiant, supernova, neutron star, and black hole. And Sun is a star of main sequence star. That is, we know that Sun will follow this path, the protostar from main sequence, and then red giant, and planetary nebula, and white dwarf. And also we know that Sun is the mid-life, that is 4.5 billion years. And after that, it will evaluate to red giant, planetary nebula, and white dwarf gradually. Now, main sequence stars are the stars which are mainly the fuel engine are the hydrogen burning, and the main fuel engine source is the hydrogen burn. And we know that if we fit the image, this is the image captured by Swinburne University, and if we know that Hertzsprung-Russell diagram, this the diagram puts the stars, all type of stars in a particular structure, in a temperature or spectral variation of their, and the mechanism, the basic mechanism of their evaluation, which entangles the basic mechanism of their evaluation. And we see here that Sun is a main sequence star, is a G2 type star. As the spectral type is concerned, it is in the main sequence star, and it is very much a main sequence star. And for that, it also falls. These are the hotter regions, and these are the less hotter regions. And this region is Sun is of the order of, if we see the temperature, it is of the order of 6,000 Kelvin, 6,000 Kelvin. And we know that a Sun, from the Wien displacement law, we know the maximum temperature, maximum peak is the lambda t is equal to constant, and the wavelength at peak will be some 0.29 centimeter Kelvin by temperature. And if we put this temperature to the of Sun as it's said in the main sequence, and we find that the wavelength is of the order of, we'll find that is of the order of 500 nanometer, which is very much in the visible region. And so we see the Sun as a bright visible region, as we can see, because with eye with eye we can see anything luminous in the visible region from the ground. Now these are the different layers of Sun, and we know that these are the different layers of Sun. These are the miles. From the core, the distance are given. This is the core. This is the radiated zone. This is the convective zone, and the layer is very thin. The outer layer are very thin, and they are composed of photosphere and chromosphere, followed by a corona. But corona is extended to a very, very wider region. Now come to the basic part, that is the surface, that is the main star. It is comprised of the core. This is the convective radiative zone, and this is the convective zone. And the process, the temperature, the density, everything is different for different layers. They are characterized. For the core, it is composed of 30%, about 30% of the Sun's radius. If I say R by Rs, it is of the order of 2.7 to 3 and 2.6 to 3, and it comprises and it uses 10% of the fuel. That is the Sun. 10% of the total fuel available, the hydrogen, and hydrogen fuses to helium, gives rise to energy. Now, This has another diagram which show how they are annular regions of the sun. This is not to the scale, please note, but there are different layers with different temperature, characteristic temperature, and different density. And the central core is highly dense, of the order of 100 gram per centimeter cube. We know that it is more denser than lead, because lead we know that it is of the order of 11 to 12 gram per centimeter cube. But it is 100 gram per centimeter cube, and it is a million degree Kelvin temperature. And fusion, the main process is nuclear fission, when the hydrogen fuses to helium, and fusion gives rise to the binding energy equivalent energy, and it is a huge energy which gives rise to a pressure, thermal pressure at the core, which withstand the outer gravity to collapse from collapsing. Now here, this is the core, and after that it is less dense, but here the energy transport mechanism is by collision only, collision, absorption, and emission process. And there is a several collision. The main free path of the plasma is very small, and it process the energy transport. It's a long time. It requires a long time to cross this region, and after that, there is a convective zone where the both type of the motion in both directions are possible, because here also the convective zone, it's just the water heated by convection. This layer corresponds to that particular region, and this convective zone is the temperature of the order of 10 to the power 6, a bit lower, and the radius is extend to 70% of the sun, and the density is much lower as compared to the earlier regions, 0.5 gram per centimeter cube. And here both the direction, motion in both the direction of plasma is observed, and it's a rotational, but rotational convection motion is observed, and energy is transported by this convection process to the photosphere, the surface of the sun. And surface of the sun is a very thin layer, the photosphere. It is 0.01 of the R by RS is 0.01 to 0.00. It is of the order of 1 to 0.001. That is a very small surface. About, if I say, that is about 250 miles or so, and it is the emission where from we see the surface, we see the observer, and observer see this surface, the photosphere. And the temperature characteristic temperature is of 5800 Kelvin. Next is the outer atmosphere, and it reveals the chromosphere and the corona. These are the outer atmosphere. Everybody, okay. Am I audible?
Yes, yes.
Now, these are the different layers of sun, and how it. Now, next come to that. This is the imagination. This is a picture, that drawing, just because it is depicted the different activities of sun. Not only the sun, different layers with activity. This is the core. Center is the core, and then there is a radiative zone. There is a convective zone, and then the surface of photosphere by chromosphere and corona. And corona, the temperature of corona, as you see, the temperature of corona is astonishingly very much higher, even higher, sometimes even higher than the core. And where the photosphere is of the order of 6,000 Kelvin. And then radiative zone, then corona, there is chromosphere, and the coronal hole it is situated above the magnetic equator of this sun, and they are less bright it as compared to the other part of the corona. And there we see the other part, the bright patches of hot gases, hot plasma, and they are stretched about the magnetic fields stretch outside the corona, and this part is as the magnetic fluxes in entry and get entry and exit from that point. They are the plasma is uh, inhibit radiation. They follow through around the magnetic field, and hence they are less luminous, and they are a darker part of the sun, outer atmosphere. Now, here is another picture of sun with the layers, the different parts of the sun, and some activities, the prominence. Now, this is the solar atmosphere at a glance by parameters: the surface gas pressure, pressure at bottom atmosphere, effective temperature, temperature of photosphere, so and so on. Sun. Now, features of sun: there is a coronal hole. This is the granulation. Granulation is the, if we boil water at the surface, we see the granules. At it start boiling, we see granules. And similarly, at the sun surface, we see such granulation. With solar wind, a flow of hot charged particles leaving the sun from towards the outer space. And another is sunspot. Sunspot, we see, this is the sunspot. It is the picture done by Vinod, and which is a joint venture of JAXA, NASA, and PARAC. And this, they are formed, we see on the surface of the sunspot that the regions, they appear and evolve and they vanish. They rotate, but at different speed with respect to the non-magnetic plasma. Because if we see that sun have magnetic field, how we can see? We can see because if we see the Zeeman effect, if we from Zeeman splitting, we observe for sunspot, and this is the Zeeman splitting image of the Zeeman splitting observed for sunspot, and for that we observe that there is entangled with magnetic structure, and this structure, this we see that umbra and penumbra. The central part is umbra, followed by the penumbra, and these are the granules. And this structure, also this sunspot rotates about the sun. But we know that there is a differential motion of the sun. The sun is a gas ball; it rotates, but it is not a rigid body rotation. It is measure the rotation of sun from equator to pole. Then we see there is a differential rotational speed, differential rotational speed at different latitudes of the sun. But more interestingly, we see that this rotational speed of, if we see the rotational speed of the sunspot, we see that the rotational speed of the sunspot is different from that of the rotational speed of the non-magnetic flux plasma. And this structure is called sunspot. It is we see as dark. How we see dark? It is cooler. How it is cool? Why it is cooler? Because there are magnetic structure, magnetic flux peeping outside, or some part it is peeping outside, and some part it is impinging into the surface and forming a loop, and the plasma is followed this loop because, and the convection is inhibited from coming outside, and that's why this part is, the energy transport is inhibited. And as the energy transport is inhibited, to some extent it is to some extent cooler. And cooler, we know that the flux energy volumetric flux and temperature is highly strongly proportional to temperature, and it is of the order of T to the power 4. Temperature, it is proportional to temperature, strongly proportional to temperature. And if this is the sun's surface to umbra, this is the temperature ratio, and it will be multiplied, it will power 4, it will be 4.8. Volumetric flux factor will be 4.8. Now there is a difference in, as the temperature is low, the pressure is also pressure is also low, because we know that pressure of a gas is proportional to temperature. Again, P is equal to nkt and N is equal to rho by mu hkt, where mu h is the mean molecular weight scaled to hydrogen and mh is the mass of the hydrogen atom, and then Pg is equal to that. If temperature falls down, then pressure also falls down. Then for this, there is some imbalance is observed at the sunspot. Then who balances it? Now there are some magnetic structure, because this is the magnetic energy density pressure which balances the pressure of sunspots. And also this we see that umbra and penumbra, these are different type of, we have peculiar structure of variation of sunspot is observed. Sizes varies. If we see the variation in size, we see there is a sunspot exhibit a broad size distribution. Very large sunspot can be occasionally reach the diameters of 60,000 km or more, and smallest sunspot can be 3500, that is 3,500 km, less than the diameter of the Earth. Then the distribution is like that. And also the lifetime in sunspot is very variable. Sunspot life for hours, and some sunspot varies for months. Then lifetimes increases linearly with its maximum size. And there is a law called Joyce's law that sunspot groups, because sunspot one leading sunspot and followed by some another sunspot, and they rotate about the equator. They rotate about the found to rotate, and these sunspot groups are tilted with respect to the equator. And the tilt angle also depends on the latitude of the point of observation. That is the latitude on which it is appears, at which it appears. And this law is called Joyce's law. It is applicable for the sunspot. And we also know that the sunspot variation, and there is a 11 years variation, minima to maxima. That is, the variation can be there is a butterfly diagram, very much known for the variation of sunspot. If we observe the sunspot with respect to the latitude, north and south latitude, and we plot it for year wise, then we find a butterfly like diagram, and this is called. And if we call amplitude, the amplitude, that is the number of sunspot, if we plot it with respect to the year, we get a figure like that. Now if we take a long period, that is the observation is 400 sunspot observation, we get a Maunder minimum here for 1950, 70, a long period of Maunder minimum. Then there is a Dalton minimum also there. There is a Maunder maximum also there. There are the different region we observe, that is weather. There is a small scale variation of weather. There is a long scale variation of weather. We know for Earth also. But there is also, for we see that a long-term variation in sunspot is observed. And these are the patches where the different colored, that is when this is the polarity, it refers to the polarity when some spot the magnetic flux is slipping out and magnetic flux is impinging into the surface. These are the polarity. And there are interesting facts about the sunspot. A typical sunspot is as big as our planet. Some have given seen are as large as 10 of our planets. Some often appear when solar storms are occurring. Some there are no sunspots on the surface, and another time there may be 250 sunspots. There are different types of, there is a 11 years cycle, and also for long period there is also some cycles are observed like that. And this is an example of sunspot. This is the real picture captured by me at 26 June 19. This is and there is a picture of sunspot captured by me, and I observed, captured by not me, but by one of the scholar here, and it is with instrument, with our instrument, and it is compared to the very observation of the NASA, and side by side there is a comparison, and there is a thus, and no. Now what we not understand, what we not understand, understand is that we don't know that the temperature, how the temperature rises so high in the corona, and what is the process in between. We don't know. We don't know how actually at what point the sunspot occurs. That's why we cannot predict sun cycle, where what peak it will appear, it will get, how much number of sunspot will observe tomorrow or the day after tomorrow. We cannot predict. These are the drawbacks. We don't know that. We know how magnetohydrodynamics. We have several multi spectrum observations are there. We have come to know with great effort. We have come to know several parameters of sun, but some are the facts we still know, like the temperature of the sun, temperature profile of the sun, the sunspot, origin of sunspot, and how the sunspot, development of sunspot. And there is, if we see, only we can say that the magnetic structure is very much, sun is a structured gaseous ball, and magnetic structure play a very important role in this region. But we see that there is a, if you see the picture of magnetic structure, picture of the magnetic structure of the sun, then we see that there are some spots where the sunspot should appear. But we see that practically out of 3 spots or 4 spots, only one place we see the sunspot. And why out of 3 or 4 magnetically active region, why particularly one region is favored, that we don't know. These are the few points we don't know about the sun, and we are constantly monitoring the sun, getting results, data from them, and analysis, and we hope that we once will be succeeded to reveal all the facts about the sun, and it will help us not only to understand, not only to protect us from the sun, but also to understand the universe as a whole, because this is only a replica, small sample of the whole universe, because the universe is filled of stars, billions of stars. Then we can also have a better understanding about that. With that, we thank you all for patience hearing. And as the reference is concerned, we are mainly inspired with the talk of the Professor Tripathi, we have already told, and some Wikipedia book, and some sites, NASA sites, especially Stanford Solar Observatory sites, and some books, and these are the reference mainly. And we thank you, appreciating your gift of time and patient hearing. Thanks. And now I end the recording. Let me end the recording.